Just made a picture on the board, and basically everything I'm going to say about this 4 lecture is about this picture. So you may recognize or not a picture that Liam drew this morning, which is close by and same but slightly different, and it's important that it's slightly different for a reason I will explain. So you did not use this, you just use bracket, right? Okay, so if you erase the red part and you erase the rotation, you recognize one of the smoothing and the other smoothing and the saddle. So this is, if you want to speak about the underlying invariant, this is an oriented model for whatever quantum invariant you care about, particularly, for instance, the Jones polynomial. Fine, and everything I'm going to talk about, even if it would not be clear today, I have this picture in mind in the back. Okay, this picture is always there, because basically most, or if not all, link homology theory you know about, meaning Knot Floer, Khovanov homology, Khovanov-Rozansky, triply graded, whatever link homology you encounter, can be fit into this picture, essentially. Preparing this lecture, I put myself a couple of rules I will try to follow. I'm not sure I will succeed, but let's figure out. So the first rule is have an open question for each lecture, have a theorem for each lecture, and have a proof in each lecture. And I didn't mess up, so inspired by this lecture of this morning, I will start with an open question that you will make sense at the end of the lecture, I guess. So open question to my So what I'm going to discuss today is this triply graded link homology. This is introduced by Khovanov and Rozansky, and also work of Fourier. I will put the name afterwards on the board, and prove that the triply graded link homology is mutation invariant, mutation invariant or mutation detector. Well, to my knowledge, this question is open. So I'm going to define today something which is called triply graded link homology. It's not known if it's mutation or not detector. So either prove it's an invariant, it doesn't detect mutation, or find a pair of knots, of mutant knots, which are detected by this pair. Okay, and okay, this is for lecture, and even if it does, and let's follow immediately my second rule. So let's put a theorem on the board. And that's the theorem. Hopefully, I will give a hint at the end of the 4 lecture how the proof of this theorem works. So a theorem, let's say, triply graded link homology detects. The N. And put a couple of names behind this theorem, because it's a concatenation of various people, work of people. So let's put, I guess that the first one is like, to put is Rasmussen. I will tell you why in a second. Then Kronheimer and Mrowka. Then Dorlin. And I will tell you a proof Potira, Robert, and Wagner. And what I want to stress about this theorem is that basically what's behind this theorem is that your favorite version of Gauche theoretic invariant, not invariant, if it's Knot Floer or Institut Floer homology, does detect the unknot. Okay, this theorem is true because, as Marco mentioned, you have application of Knot Floer homology to low-dimensional topology, and in particular, it does detect the unknot because it does detect genus. And basically, I'm working on the other side of the word. I'm working on some algebraic setting that you will see in a second, and it's quite surprising that such a purely algebraic defined invariant that detects the unknot is kind of surprising, and this is used a couple of spectra seconds. So let me comment on the name here. So what Rasmussen proved is that there's a relationship between what's something I will define today and the Khovanov homology Liam talked about this morning. So there's a relationship between these two homology, and then Kronheimer-Morfka proved that Khovanov homology detects the unknot using something which is we not talk about this week and probably not with you before, which is called Institut Floer homology. So it's another version of Floer type homology. Dorlin proved a null conjecture saying that Khovanov homology is related to the Knot Floer homology, and as such deduce that Khovanov homology detects the unknot. Concatenating with Rasmussen, the triplet it does as well. And during this lecture. Okay. Fine, that's for Dorlin, D-O-W-L-E-N. Kronheimer-Morfka. Olatov. Beliakova. Robert and Wagner. You may know probably both of, I mean, you may know everybody actually in this list. Okay, fine. Okay, so let's start. The reason I want to put myself doing theorems and proof is that most of this, everything is actually we're giving the right definition and having the right definition. So we spent many times like giving a definition, another definition, and so on and so forth. So I mean, you have to constrain yourself to give proofs. Otherwise, I'm just going to give you a list of definitions and tell you, we have this definition as the right one, and it works. Perfectly fine. So for all this lecture, n will be an integer, eventually 0. K will be an integer which is strictly bigger than 0. And R will be a commutative ring with units. For today, R will be 0. Okay. I mean, link homology theory has been created like more than 20 years ago. And now people start studying very deeply, or more deeply, let's say, what's happening if you change coefficient. So people didn't pay attention at the beginning, like working over Z2 coefficient, working over a field, over Q, over Z, what's happening. And people didn't pay attention for a while. And now the more we know about, the more we care about how universal or how precise can you be. Okay, RK will be then Z. So it's a polynomial ring in k variables, and fine, and I will also denote it like Z of X underline. So RK is graded, and the degree you choose for the variable, you may complain, but that's traditional. Xi is of degree 2. And this is true for I equal 1 to k. And this is called, sorry, this is graded, this is what we call, this is a Q degree or quantum degree. As the title suggests, they will be triply graded, so pay some attention about what the grading are. Or at least I will try to. So this is traditionally called the Q degree. This also show up somehow in Liam's construction of this morning, even if he did hit this question for the moment. And about the things you care, just to something I will call, so if you have something which is graded and with a Q degree, I can compute something Q dimension, so the dimension as a graded abelian group, so over Z. So the Q dimension of Rk would be 1 over Q square to the power k. You can think of it. In degree 0, you have just 1, and in degree 2, you have x1, x2, xk, and so on and so forth, and just figure out this is the case. Those things I need, which already show up in my blue box, is I need something which is called the shift, which is a Q shift. Well, it used to be in literature for shifts using other brackets. So not to confuse with any other brackets. I will not using brackets for the shift. And I'm just using this convention that something I will call Q of L Rk. Okay, so that's the shift of L shift of the ring Rk. And just that you recall my convention, I just make it as transparent as it is, that the Q dimension of Q to the L Rk is Q to the L 1 minus Q square to the power k. I just shift the variable shift. And L in this shift could be any integers. So far, so good. Something I will call Rk hat will be just Rk tensor with itself over Z. And this is isomorphic to something I will denote Z of x1 xk, x1 prime xk prime. And by this, I want to recognize, so this is, you can act with Rk either on the left or on the right. So this is a Rk bimodule. And the fact using the isomorphism with a variable x and x prime, I just want to recall that this is the left action. And this is the right action. I'm just using, I'm not using this convention because I think it's more comfortable for those computation, understand what's happening if you are not familiar with using bimodules. But actually in the literature, people mostly wrote and play around with this, and I will do as well, but just to make it clearer, I will do, let's do the same obvious things. So this is Z of x prime hat. And let's make stupid comments like Rk is Rk hat modded out by, I will recognize the left action to be the right action. This is also Rk. Of course, Rk is a Rk bimodule, free of rank 1 generated by 1. Very good. Okay. Maybe, no, I don't need that. Fine. Okay. So beam K will be the category of graded Rk bimodules. So in word, object of this category are Rk bimodules, and morphism in this category are just Rk bimodule maps. sorry, it's a commutative ring. I mean, there's nothing non-commuting. Yes. Other questions? Fine. Most naive comments. So if B, so my letter, which is very much used, will be B. I'm going to use it for various reasons. It will show up in a second. So if B is a bimodule, if B is an RK, bimodule, then you can look to the tensor product of B over RK, and this is another functor of the category. If you give me a bimodule, I give you another bimodule, and it's well defined with maps as usual. So this is another functor. Of BMK. Okay, tensoring with a given bimodule. Very good. Just that I don't forget anything. Very good. My next notation will be that one. So com/h, which you use this morning, /h? No, not yet. Okay, so these are complexes of RK bimodule modulo homotopy. And just to make our life easier today, this is bonded complexes. So this is a category of bonded, well, cochain complex over BMK. Very good. Fine. So I will need, as said, a couple of gradings. So I already introduced the grading. So the Q grading is usually called internal. So it really does depend just on the bimodule. So I will play with the category of of complexes. And one of the grading is just the homological grading or the cohomological grading by convention. And again, well, there was a discussion in Marco's talk about conventions, about red and blue curve, alpha curve. I must say that for the triply graded link homology, it's worse than anything. You choose a paper, and the convention is different from the other one, and different for the other one, and the other one, and for the other one. There's no global convention, so I make a choice. You may complain about this choice. And if you want to look to the literature, then it will not match the choice. You have to find a way to understand yourself what the convention you choose. Okay, very good. So if C, let's C be a bonded complex, a bonded complex of RK bimodule, then as before, I'm just saying tensoring with this chain complex over RK. This goes from homotopy category up to BMK into the homotopy category over BMK. So tensoring with this complex of bimodule is another functor. And again, you tensor over RK. So as another functor of the homotopy category of RK bimodule. Okay, now what else do I need? I need shift in cohomological grading. Cohomological grading. So C as before. So C is a complex of bonded RK bimodule. So sorry. This has been recorded, yes? For the memory, good. This is now done. Okay, so as I said, I choose the homological, so that's my C, the chain complex. Ci and Ci plus 1 are RK bimodule. As usual, the indices tell you in which degree they are. So this is in degree I, and this is degree in degree I plus 1. And then what I denote TLC, so L is again an integer. So this will be the same thing, Ci plus 1, blah, blah, blah. And this is living in degree I plus L, and I plus 1 plus L. Okay, and again, this is a choice of convention. I mean, if you go into the literature, and you probably never thought about it, but shift in cohomological degree or in homological degree is a nightmare. And the fact is that in classical algebraic topology, there are reasons for the definition. In this setting of link homology, you choose whatever you want. I mean, there's nothing behind conceptually. So you choose cohomological or homological grading, and you choose the way you write down the shift. So I'm just telling you the way I choose the shifts. Okay. This is all definitions. So I had already a theorem, but I basically told you I will not prove this theorem today. And hopefully I will prove it at least actually at the end of the 4 lectures. So for the moment, there's absolutely no topology at all anywhere. And the other thing I should eventually have before starting is that if you go to the website and look for lectures on link homology, usually what people do, and Liam did this morning, you start with some of the old story of the 80s of your preferred Jones polynomial or Humphrey-Petit polynomial or choice. So I made the choice, probably the wrong one, not to do so. And so Liam, successfully Liam just did what I don't want to do. So either you know what the Jones polynomial is and the Humphrey-Petit polynomial is, and then you're fine. And you don't know what triply graded is. And then you learn something from here. Or you don't know what the Humphrey-Petit polynomial or the Jones polynomial is. And you will learn what triply graded is, and I will tell you, that's fine. Then you know also what the Humphrey-Petit polynomial is, or the Jones polynomial is. And both of them are fine. But I just want to move on as quick as possible to something. So the reason of this construction, what I'm completely hiding, I mean, there was reason to expect this construction I will describe today. And I'm not telling you why to expect this construction. I'm just giving you the construction and tell fine. No, play with that. Fine. Very good. So what I want to discuss, one of the names I mentioned just before. Why I'm missing something? No, I need something before. So yeah. So that's my other B. I will do a double bar, which is not usual at all, but since I'm losing it less than the other B, I prefer to choose that one. So this is just the braid group. Sigma 1, sigma k minus 1, generated by usual things. And again, sigma I, sigma j is sigma j, sigma I. If I minus j is strictly greater than 1, and sigma I, sigma j, sigma I is equal to sigma j, sigma I, sigma j, if I minus j are at distance 1. So this is a braid group. On K strands. Very good. And now I can discuss something which is called Rouquier complexes. For this, define Bi to be, so this bimodule, RK hat. Remember, I will think of it as variable x1 to xk and x1 prime to xk prime. And then I mod it out by xi plus xi plus 1 is equal to xy prime plus x1 plus x1 prime. The product of the non-prime is equal to the product of the prime, and otherwise xj equal to xj prime if j is not 1 or minus 1. This is sometimes called a Bode-Samuelson bimodule, or a Soergel bimodule if you ever heard of this. And this is, I'm just choosing to shift this bimodule by q minus 1. Okay, and another way to present this is you take Rk, you tensor over Rk, but then not over just E, as I did before when I defined Rk hat, but then over Rk Si. So what is Rk Si? This is the polynomial in k variables, which are invariant under the action of the transposition Si. So meaning symmetric in the variable xi and xi plus 1, which is xi plus xi plus 1, and xi times xi plus 1. These are a generating subalgebra of symmetric polynomials in variable xi and xi plus 1. So these are just exactly the same, and for convention setting, I'm again putting a q minus 1 here. Okay, just to stick to this q minus 1. This has a generator, let's stick it here, 1, so the constant polynomial 1, which was usually in degree 0, is now degree minus 1. This is my convention of shift. Yes? Rk is a module over itself, or a bimodule. Yes? Exactly. I mean, this is why I put the left side. Here you just have, this is clear Rk, I mean, a bimodule in the variable xi and xi plus, sorry, xi and xi prime. And just injecting the quotient, and this doesn't affect the action by the x primes or the x. It's fine. This is a bimodule over the xi and the xi primes, which means this is still a bimodule over Rk. And this is precisely the same. Good? Yes? So Si, okay, let me, okay. So Si is a transposition of the symmetricum K letters. And it does act, I mean, Si of P x1 xi xi plus 1. I hope this is clear. This is just P of x1 xi plus 1 xi. The Jackson polynomial with transposition. So these are just the symmetric polynomials in variable xi and xi plus 1. So E1, which is xi plus 1, and E2, which is just the product of the two, and that's it. And then since it doesn't affect, this action doesn't affect the rest of the variable, then nothing happens to the rest of the variable. Good? Other questions? Very good. Okay. Now what I want to do is start drawing pictures. Because, I mean, I will continue with algebra a little bit, and then I will start doing pictures. So the way I want to think this BI is precisely with this picture which is still on the board here. So let me be more precise than this. So this is meant to give a pictorial definition of the BI. So the variable, let's hope I didn't mix it. So the variable on the bottom are the xi prime. So maybe let's stick to the xi. Okay, and this is the prime. So that's the variable on the bottom. So it's the left action with the prime. And the top action. I did mix left. Yeah, sorry. If you don't mind, I prefer to correct. Here. Because, yeah. Sorry for that. But thanks for the comment. Okay, so this is the xi minus 1, xi plus 1, and so on. Yes, I'm reading braids from bottom to top. There's also a convention that you have to choose at some point. and the way you think about this picture exactly, so you want to think of this picture, let's say, as z of x1, xi minus 1, xi plus xi plus 1, xi plus 1, or maybe, yeah, okay. Xk, and this is xi plus 2. Let's put double prime just so that you don't be confused. And what these pictures aim to say is that the symmetric polynomials in the x double prime does embed with natural identification at the bottom and the top. And so the output is that you can ignore these double primes. This is why they do not show up in this definition. Because the only thing you have to remember is that this is telling you that the symmetric polynomial in the xi plus 1 prime and the xi plus 1 have to agree. This is what is telling you at the top. So this means that this, you should think of this RKSI as living just here. Okay, what has to cross by? So this is RKSI. This is a version at the bottom of RK, and this is a version of RK at the top. So what's allowed to pass through this tensor product are just the symmetric ones in the variable xi and xi plus 1. Is that okay? Again, this is just a picture, meaningful. So this means that, yeah.
It looks like you have an inclusion, that I understand, but also projection.
No, also an inclusion on the other way around. I mean, you do include RKSI on the right-hand side and on the left-hand side.
Yeah, but in your picture, it looks like you have projection from RK,
No. It's really an injection. Actually, you do inject RKSI on both sides. It's not a projection.
The picture is also bottom to top.
Yeah.
Like you have also had some canonical thing from RK hat to the middle part, which is actually
Yeah, no, it's just a matter of if I was drawing from not from bottom to top, but no, left to right, you will not complain. Because no, because then it's just RK in the middle, SI in the middle, which is either a left RK model or a right RK model.
in your picture.
Here, yes.
Picture. Can I decompose the picture into two pictures, one from the bottom to the dotted line, and one from the dotted line to the top? That's my picture.
So let's see. This is Z of x1, x2, and this is Z of E1, E2, meaning the embedding of that guy. So this is,
Yeah, but I want to read it from bottom to top. You also have, no, the same. Anyway, okay, that's fine. Thank you.
no, I mean, it doesn't matter. This is a matter of being a left or a right module on the full ring or on the symmetric ring. This is the only thing you should read from this picture. Here I'm thinking of this as Z of x1, x2 as a left Z of x1 model and a right Z of E1, E2 model. And then I'm doing it the other way around. And then I'm identifying the middle action on Z of the equal. So if you call this, I don't know, if you call, is that okay? Both of them are bimodules. There's just no, there's no morphism. No, I mean, okay, maybe because I should say that for people who know this picture represents usually morphism in some representative version of whatever quantum groups you want to play with. And this is exactly what I'm skipping. I'm not telling you this part of the story at all. I'm just pretending that this is in the back and I will avoid that. Okay, but no, this picture for the moment are just bimodules. The bimodules, the maps for me will be coming from whatever forms will be at the end of the day. Any other questions? Please do so, because this is kind of very important for whatever will continue after. So I hope this is clear now. Now we're going to talk about the maps. So I need the maps. For defining what's so-called Rouquier complex. So that we don't note double bracket generator sigma I is by definition the tensor product with this length complexes. So 0 goes into Bi, goes into RK, goes into 0. Fine. Then if you, and what is this map? This map is doing nothing. It's sending 1 to 1. Now you just have to be careful that since I mess it up and I put this shift here, this is just Q minus 1 in order this map to be Q degree preserving. Because remember the 1 in BI was in degree minus 1, so I want the 1 in RK to be as well of degree minus 1. Then I have to tell you the cohomological degree I'm using. This is 0 and this is 1. This is the cohomological degree. So fine. I will define someone which is sigma for sigma inverse, which by definition is a tensor product of someone which goes the other way around. So Rk goes to Bi, goes to 0, goes to 0. This is in degree 0, and this is in degree -1. I have to tell you what the map is. So the map is sen1. So remember, this is a free bimodule generated by 1. Just I have to tell you where 1 goes. If I tell you where 1 goes, then I'll tell you what the map is. And I'm sending, for this picture, let me check, I choose this command. No. Okay, xi goes to minus xi plus 1. Fine. And now if you think of degree, something is wrong. This is of degree 2, because if there was no shift on Bi, this would be of degree 2, because I'm sending a degree 0 to a degree 2 element. Then I'm shifting down by -1. So this is now of degree 1. And I have to, so I have to adjust somewhere in order to be of degree 0. And what I do is I shift down, I shift up as a source, which again put everything in degree 0 as well. The non-obvious part, which is an exercise, is checking that this is really a bimodule map. Okay, exercise. Check that these are well defined bimodule maps. Slightly more tricky. Yes. This is bimodule, and let's call this unzip for a reason which is, yeah. And this is zip. And if you want to know why I call it like this, look to the picture on the top. Okay. Yes. And slightly more tricky, complete complete them into short, exact sequence. Of bimodules. This I'm in particular suggesting that one of them is injective and the other one is surjective as a bimodule map. And I'm just asking, tell me what the kernel is to see what happened. And yeah. Theorem. Which is due to Rouquier at the beginning. The map which go from the braid group into the autoequivalence of this complex of bimodules, which sends what you expect. Sigma I goes to sigma I inverse goes to sigma I inverse, is a well-defined group homomorphism. Okay, and then I would like to discuss the proof, or at least a part of the proof of this theorem. Okay. Another way to say it is to say that the braid group does act on this category. Autoequivalence. So these are only functors which are invertible. Is that okay? I say it again. If I don't write it, it's only functor of the category which is invertible in particular, which has to be, because if you want this to be a group homomorphism, this is an invertible element, so I need to say it. An invertible only functor of the category, and invertible only functor are called autoequivalence. Sorry? Yeah. Okay. Good. I will try to sketch part of the proof of this theorem. I must stress that Rouquier original theorem was way more general than what I'm stating here. And the reason being is that the braid group is the first of is one of the what's called the Artintis group. And Rouquier theorem has a validity for all finite Artintis groups, whatever you know what it is. Okay, and so there's a more general construction which is working more generally. Oh, fine. So the first question we have to ask ourselves about the proof of the theorem is, what is the unit? What is the one on the right-hand side of this morphism? So what is the unit for the autoequivalence of the homotopy complex over beam K? So one, so proof, or more or less proof. What is one? Okay, let me not rewrite what is here. What is this one of the automorphism? So this should be something, when you translate it with it as a complex of bimodule, doesn't change anything. So I could have this as this for the bimodule before our homotopy category. So the unit for RK bimodule is just RK as the bimodule. You do nothing. So, and then you don't want to affect the homological degree, so you don't want to affect anything. So one is just, by definition, 0 goes, so it's contouring with 0, RK 0 in degree 0. Sorry? No quantum shift. No, here you really want just that. Okay, fine. Let me. Is it true? You're asking if the group of autoequivalence of the.
When you know what is the identity, and you know that this thing will be the identity.
Yes.
That's all we really say, right?
Yes, that's the only thing we are saying. If you're asking, do I understand completely the group of autoequivalence of the monad categories, the answer is no, I don't understand that. I understand elements which are in that, and I'm going to tell you that this is one, and these two there are two other elements which do live in this invertible people, and then any transport of these people, as you may, up to natural transformation. I mean, as on the functor are equal up to natural transformation. So this, I want to say, let me rephrase it, these complexes, I'm looking for these complexes up to homotopy. If two complexes are homotopic, then they do induce the same on the functor, because there are natural transformation between them. Is that answering the question? So everything I'm going to do is complex of bimodule up to homotopy. If you have a if you look into this complex up to homotopy, then tensoring with it, I'm pretending this is a unit. No problem with that. And it's even more, in that case, it's even better than up to homotopy. It's just an isomorphism of complex of bimodules. There's no homotopy to take care about. But for the other cases, I will see, then you need to take care about homotopies. Is that all right? Okay. 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 Let me try to do this. I will do the short version. Okay, so these are bimodule maps. So this the claim is the claim is if you send 1 to 1, yeah, okay. Don't let me not be precise here. I'm pretending that there exists. A short sequence which looks like this. So you have a way to embed Q minus 1 BI into BI tensor BI. There is a surjective map from here to here as well, and the kernel of the one is the image of the other one. And actually, multiplying this map by scalar, there's only one map you can find. So this is one I don't need to, I've seen I'm out of time. I'm not precising what this map are. I start writing here, then I just tell you what's fine here. So for degree reason, the only map you can imagine here is 1 goes to 1. You just have to take care of degree. This is why I spend some time taking care of degree, because degree tell you a lot about what are the actual flexibility you have in defining maps or not. And most of the time, you don't have choice. Okay, you have only one map which has the correct degree, and that's it. And this is an important exercise to guess what this map is. So you need a well-defined bimodule map going here for here, and I will solve this. If you come to the exercise sessions, and I will tell you, I will at least tell you what this map is. It's also, and there's an additional thing which is split. Proof exercise. Okay, fine. So let's draw a picture for that. Then I will, for this short echo sequence, again I will do pictures. Because it's more useful and more convenient for most of the time. So this is just BI. And this is also just a BI. Okay, this is meant to be BI over BI, and just because I will not precise here, this is over RK. Okay, I have a BI, and I identify the left action of one with the right action of the other over this RK, which is here. And here you have a Q minus 1, and here you have a Q. Okay, what this map is doing, I just told you, is doing nothing. So the question is, what is this bimodal doing? If you give name to variables which are here, okay, just give names to this variable, as I was doing before. This is, I recall, this is primes, these are the non-primes, and I just rename the variables here double prime. This is xi double prime, and xi plus 1 double prime. And what I do care is action on the top by xi plus 1, and this is xi prime, xi plus 1 prime. Okay? I act on the left with the prime, I act on the right with the prime. This is telling me that I do identify the symmetric polynomials in two variables, double prime with the top and the bottom variable. And that's the relation I'm adding. If you want to rewrite everything, you can rewrite everything as a polynomial ring in three sets of variables, the primes, the double primes, the double primes. And this is just telling you what's the identification, what's the ideal you mod out to make the identification. Okay? And now think about what's happening for the double prime. If you have a double prime, either you have the variable x, either you have nothing, so meaning you have 1 on this side of the tensor. Then there's nothing you can do. Or you have a double prime with just one double prime, either on the left or on the right, or eventually you have more complicated things. So what I'm telling you to do this exercise, the hint, what you have to understand is the following easy thing, which is a rank 2 free module over the symmetric ones in two variables. Okay? Of basis, if you want, 1 with this notation, 1 xi double prime. Okay, I'm just saying that polynomial in two variables can be written as, uniquely written, as a symmetric polynomial plus one of the variables times another symmetric polynomial. What I would like to stress here is that in the literature, there are complications with coefficients, which do come from the fact that most of the time you want 2 to be invertible, and I'm stressing that everything I'm doing here doesn't require 2 to be invertible. This is over z, and everything is valid over z. Okay, since I'm running out of time, so what I plan to do today is, let's see, yeah. I'm planning to do it to continue this proof. Okay, I'm really running out of time and I don't want to push for it. So you can think of it about this proof. I mean, at this point, what I would like to stress is that a priori it's hard to guess this definition. What is hard is this. Proving that they do the job once you know they are the right things is not that difficult. I mean, it's not only, not difficult. It's just, at the end of the day, it's just homological algebra. Okay, everything is explicit. There are bimodules maps you can compute. You can, as Liam started to do this morning, you can compute homotopy, chain maps. Everything is explicit. And I will do that for you tomorrow. I mean, proving explicitly that this theorem is valid in full generality. And I think I'm just going to stop before running out of time.